Hello, everyone. Thank you all for joining. My name is Daniel Davlos from Cal State University, Los Angeles. And today we're going to go over the district case of Ball State University. Next slide. So before I begin, I just want to give a little brief introduction about what exactly is the Solar District Cup. And what it is an educational competition, which is actually hosted by the U.S. Department of Energy that actually challenges students to model and design a storage system, either to a campus or urban district. Next slide. So these are actually the breakout of the teams that we have decided in order to make this design system more efficient and the roles and responsibilities that were assigned. Next slide. So the district case that we're assigned is from Ball State University, located in Muncie, Indiana. And the main objective is to make sure that we created an energy storage system that maximizes the energy offset, as well as to save the university a financial savings over a 20-year period. And as you can see, the ones that are highlighted in red is the area for the campus and the areas that we can use to design. Next slide. So without further ado, I'm going to hand it off to Nobob, who will go over the conceptual design system.
Hi, my name is Nobob, and I'm in charge of the conceptual system design. Today, I'll be giving you a summary of our PV system performance and site layout. So before I reveal our site layout and our PV system, I'd like to show this preliminary design drawing that we developed in the early stages. The main purpose of this drawing was to highlight the areas of the campus under consideration for PV installation. And I'd like to bring your attention over to the top right of the slide, which shows a large plot of land in which we were encouraged to design a large ground mount PV system that will interconnect to the distribution line. And next slide, please. And this is exactly what we did. We have designed a large 3.5 megawatt ground mount PV system in the plot of land north of campus. This site layout, which was modeled in Aurora Solar software, shows all of our solar panels, inverters, a transformer, and our chosen battery, the Tesla Megapack. Amongst the countless simulations we performed, this 3.5 megawatt PV system yielded the greatest energy offset and financial savings. Next slide, please. The PV module we decided to use for our design is a 330 watt polycrystalline solar panel manufactured by Axitec. It has an efficiency rating of 17%, and using these panels, our calculated system price per watt is $1.71. We made several other module considerations, but the Axitec modules proved to be more cost effective. Our selected inverter was a string inverter rated for 15 kilowatts and manufactured by SMA Solar Technology. Next slide, please. Here's a summary of our site characteristics. We're installing 10,500 Axitec modules in a 7.5 acre area with a fixed panel tilt of 22 degrees. The panels were laid out 48 inches apart so that shading from the next row would not be an issue, and thus power optimizers were not required. This is also why only 56% of the area of land is utilized for the solar panels. We wanted to ensure the best solar panel efficiency and avoid shading issues. Next slide, please. Here's our system single line diagram. We have a total of 208 string inverters, which will each have its own subarray. Each subarray will have a maximum of 13 and a minimum of 4 modules per string. The conduits will branch out from each inverter and be embedded in the soil, leading to the main distribution line to provide solar power to Ball State. Next slide, please. Here's a block diagram of our 3.5 megawatt PV system. We have our panels connected to a fuse disconnect, leading to the inverter and ultimately to the main AC panel downstream in to the university-owned substation. We have also shown the Tesla Megapack, which is an impressive 3 megawatt lithium-ion battery storage unit. Next slide, please. And this is a summary of our simulation results. For the purposes of this simulation and for comparison, we decided to use the energy consumption data for the Noyer complex, which is a housing facility at Ball State. Our PV system yields an annual production of more than 4 million kilowatt hours, resulting in a 67% annual energy offset for the Noyer complex's annual energy consumption. We'll discuss in our financial analysis section just how much savings are generated from this installation. Next slide, please. So here's an hourly load profile for NORA complex for the year. The peak energy consumption occurs around 2 to 3 p.m. and reducing the energy consumption during these peak times and using the energy produced from our PV system will yield the greatest financial savings for Ball State University. Furthermore, with the introduction of the Tesla Megapack, we can implement a peak shaving strategy. And we can set a threshold of 900 kilowatts. And whenever the hourly consumption goes above that threshold, the battery will provide the rest of the power. Next slide, please. Finally, here's the specs for our battery storage unit, the Tesla Megapack. We made several other considerations for our battery, but the Megapack was the best one for us. For our system, we only need one single Megapack unit, which has a usable capacity of 3 megawatt hours. It has a 90% efficiency rating and also has 100% depth of discharge. Next slide, please. One of the benefits of this, of the Megapack is that it requires 40% less space than typical battery storage units of this size, and 10 times fewer parts. So this modular system can be installed cheaper and faster than current systems. Going off of the peak shaving approach I mentioned earlier, the Megapack can discharge at times of peak capacity to reduce the peak loads and demands on the distribution infrastructure. Now I'll be handing it over to my teammates, Kevin and Gabriel, who will provide a summary of the distribution system impact. Thank you.
Thank you, Nobab. So the distribution system simulation and analysis were tools that provided us useful information to attempt designing and operating a distribution system. Common distribution use cases that we tried to take advantage of were peak load management, impacted distributed generation and storage, evaluation of distribution and automation design, design of protection, estimation, operation, and maintenance costs. So talking about overvoltage, by researching this, we knew that overvoltage occurs when the supply voltage rises above the rated voltage of the equipment or motor. The overvoltage can cause excessive current to flow as well as creating excessive voltage stresses. So we try to mimic or simulate a possible case such as that to our design. We try to use different software applications such as MATLAB, for example. But when we try to use the MATLAB toolbox that communicates with the OpenDSS, hoping it would make this situation simpler, but we could not get it to fully function, unfortunately. So we mainly focus on just using OpenDSS, which the software was actually recommended by the competition. And that's when we tried to model the PV and storage system with parameters. And now I'm going to pass it off to Kevin, who actually explained about the process.
Thank you, Gabriel. So again, as mentioned before, OpenDSS is a software simulation, which allows us to evaluate what's going on within the distribution network. For this part of the project, our goal was to use OpenDSS and model the PV and storage system that was designed earlier. So in order to do this, we needed to run the base case that was provided by Ball State University and obtain the base data, to then which we would modify by adding voltage and thermal limits, with then afterwards slowly incorporating the PV system itself. Once the simulation was ran and compared to the base case to analyze any voltage and thermal issues, this would have to be repeated for a PV inverter case and along with our storage model case. If there were any violations, you would have to identify a solution in order to resolve these issues. So prior to beginning, new lines were added to the existing system that would extend from West Bento Avenue to the Tilton Avenue. Afterwards, the PV and inverter parameters were then incorporated into the software. However, after running our initial PV case, we ran into issues and spent numerous amount of time in trying to find a solution to get the simulation run correctly. Unfortunately, at the end, with the limited resources that we had and the new exposure to the software, we weren't able to run the cases successfully and the simulation and obtain the results that we wanted. I will be passing it on to Brian for the financial analysis now.
Thank you, Kevin. Regarding for the presentation, BSU's case actually owns and operates its own distribution system downstream of a university-owned substation that connects to the utility, which is Indiana Michigan Power Company. So they're a little special. We used a system advisor model, the software that's provided by the Solar District Cup, to run a simulation. Here's next slide. Here's a little breakdown of the utility rate. They charge, the rate goes up after 410 kilowatt hours. There's a small service charge. There's a base rate charge as well. Next slide. So this is for the Neuer complex energy bill summary. So BSU actually gets charged $14.72 on their peak, which is 3,200 kilowatts. And after that, they get charged 1.088 cents for their total energy consumption for kilowatt hours, which is 470,000. And their for January, their highest bill, consumption bill, is over $52,000. So we found out that Indiana, as it gets pretty cold in December and January, that those are their most months that they consume power. Next slide, please. So this is a little summary of what our panels and power storage system did for their bill. From January, as you guys can see, it went over from $52,000 down to $2,192. This is just for what they'll be paying for their utility bill, as it drastically decreases. Next slide, please.
Seems like there's an issue going on.
I'm going to intervene just for a second to reset the controls. Okay, try again.
Thank you. Sorry about that.
So this is our system cost. This is our system cost estimated financial savings. We estimated from our modeling and our own calculations, as Sam wasn't completely accurate, we got down to our cost per watt at $1.71. Our 20-year utility billing savings, just for their billing, for their bill per, for each year, we'd be saving over $8.6 million. The total system cost, including the batteries, storage batteries, would be almost $6 million. So the actual savings without any government incentives and tax incentives would be the 20-year utility billing savings minus the cost, which is a little over $2.6 million. So for the sake of this presentation, we had to do a PPA since the BSU doesn't want to pay for the whole system outright. The PPA purchase rate that we decided we should negotiate is 7.4 cents, so we can actually pay off the system in 20 years. Next slide, please. So this is just a summary of what a PPA is. This is a financial analysis cost breakdown. In Indiana, one of the nice incentives is that they don't charge sales tax on any commercial solar investment plans or solar plans. So all the equipment that we would buy wouldn't have sales tax on it. So generation equipment's $3.5 million. The Tesla battery cost would be $800,000. Installation and some miscellaneous costs that we factored in would be $200,000. And some of the eligible government incentives that we calculated would be around 1.3 million. We set the annual panel degradation at 0.5%, and solar investment tax credit given by Indiana, we've set at 30%. Next slide, please. And this is some cash flow projections that we got from Sam, the software we were using for the PPA price. This is just 1 through 10 years. Next slide, please. And then this is the rest up to 20 years. This is some more analysis data from Sam. It actually gave us the initial cost, which was actually very close to what we calculated, a little over $6 million. Yeah, next slide, please. I'll hand it over to Mo for our development and construction plan.
Thank you, Polly. For the development
I'm
plan,
sorry to interrupt you, but you have reached the end of your 15-minute presentation time period.